In the compensator system, a steady state error a little will be changed because we have the GSC. And as you know, the GSC is equal to Z plus ZO and S plus PO. And if S go to the 0, you find the ZO PO. And as you know, the KAP is limit of the GS and the K prime P, because for the compensator will be put the K prime P is equal to ZO PO KP. And the same thing for the K prime V and the K prime A. In order to maximize the reduction of the steady state error, but with ZO close to PO, ZO and the PO have to close to origin, then you can say maximize reduction of the steady state error. For example, if you have a GS is a system of the radar 1SS plus 2, if you put the ZO is minus 2, PO minus 1.9, a little far from the origin, you can find 0.5. The steady state we have, but a little bigger than if the steady state close to origin point. If you put the ZO minus 0.2 and PO minus 0.1, and normally we choose ZO very small, then we can find the PO. This example, they ask us to find the lag compensator with steady state error is 0.56. As you know, this is the steady state error, the previous one, uncompensated, and they work in the steady state error. They use the lag compensator or PI controller. With the overshoot 3% very fast, you can find the sigma. With the TS, you can find the omega n. Then you can write the SL minus 1 plus minus J 0.88. They ask us ZO, PO, and K. The K is exactly the same as the previous one. You can calculate is equal 1.77. For PO and ZO, arbitrary small, usually 10 times smaller than the SL1. This is a very important sentence. Usually 10 times smaller than absolute value SL1. We know if V is equal to 1K ZOPO, and this have come from the system 1 divided by S plus 2. When the S go to the 0, you can find the half here. If you put here, you find the 0.56, that this one they give us. You choose the ZO very small, 10 times smaller than SO, then you can find the PO. In this figure, they show us the uncompensated and the compensated system with the lag compensator. With the step unit, you see the result. Another example, KGS. This is the K, this is the GS. Reduce the steady state error of this system by a factor 10 using a lag compensator or lag controllers. Find which error, E position, E velocity, E accelerator. Find the value of this error. Deduce the new error required to satisfy the specification. Compute the steady state error for the compensator system. Compute the pole of the compensator. In easily, you can find the EAP equal limitation of the S1 1 plus KGS. This is the RS. RS here is a unit, is 1S. EAP become 1 plus KGS. And we know the K is equal to this value. We put the K in value. S equal to 0 become 1, 2, 10 become 20. This value become this multiply 20, 1 plus, you divide it, you can find the EAP. They said to us a steady state error a factor 10. The factor 10, that means EAP divided by 10, you can find a prime P. With the compensator, that means with the lag controller,